It's coming. Yeah, great. It's recording. Oh, camera off.
Yeah.
Oh, yeah. Okay. Yeah. Good. So there we go. Okay. So, yeah. Last lecture we were doing gamma function, right? So I started. So we defined gamma function and established some properties of gamma. This was our original definition: 0 to infinity, e to the minus t, t to the s over t dt, and we check that this integral is convergent for real part of s bigger than 0, right? We check that, and we also check the functional equation gamma of s plus 1 rather equal to s gamma of s, right? We also check that gamma of n is equal to n minus 1 factorial. Check this. We calculated gamma of half, gamma of 3 over 2, and this sort of things as well, but doesn't matter. So morally, then gamma of s you should think of as s minus 1 factorial. This is the idea. Would be nice to say gamma of s is equal to s factorial, but no, it's s minus 1 factorial. There is another function where, like, called pi of s, which is s factorial, which is gamma of s plus 1. That's the way things are. So anyhow, so Riemann, I believe, used pi of s, but that's, now this is the more standard usage of factorials. Okay, so now we want to analytically continue to the left half plane. So the idea is analytic continuation to real part of S. Actually, what we are going to show is that it can be analytically continued to C, take away 0, minus 1, minus 2, minus 3. So we can, now I'm going to show that it can be analytically continued to all complex numbers except negative integers and 0. Okay? So how we're going to do that, where the thing is here. I mean, this is like our savior, because this relation star implies that I can define gamma for real part of S bigger than minus 1 by this relation. So for real part of S bigger than minus 1, yeah, I can define here gamma of S to be equal to gamma of S plus 1 over S. Here is the formula. It works because for real part of S bigger than minus 1, gamma of S plus 1 is real part is bigger than 0. So that's in the domain of gamma now. So I can take the gamma, divide by S is okay. So we go like that. But there is one point that we have to miss. We have to avoid, that's 0. Because this 0, S different from 0. Okay? No, if we need S plus 1 real part to be bigger than 0 in order to use the original definition of gamma for that, right? So we just call it. Yeah? Right. So this is so far what we did. Now let's see. What we did so far, we extended the domain of gamma to everywhere to the right of the part line real part of S equal to minus 1, except 0. Right? except at 0. Now 0, we know what's going on at 0. So what is the situation at 0? In fact, 0 is a simple pole for gamma. So I just write it, note, s equal to 0 is a simple pole of gamma. I mean, the reason, of course, is that at s equal to 0, gamma is totally regular around 1. It's a holomorphic function around around 1, right? Here, gamma is holomorphic, right? So you can expand this easily. So gamma of s plus 1, you can expand it, and it's just and its value at so let me write it. Gamma of s. So this value at s equal to 0 is 1. Gamma of 1 is 1, right? So this is 1. So this is of the form 1 over s at s equal to 0. So it means that this point s equal to 0 is a simple pole with residue 1, right? So let me write it. With residue of gamma at s equal to 0 equal to 1. So far we are okay? Okay. Then we can continue the process. So how am I going to continue to minus 2, for example, here, to real part of s minus 2? So next, extend to real part of s bigger than minus 2. Well, we just use the same formula, because here is gamma of s is equal to gamma of s plus 1 over s, and we can just use the same formula, right? Again, use a star. Now, the one thing that's rather unfortunate is that for all these extensions, I'm still using the letter gamma to denote all these extensions. So it may create a little bit of confusion, but I hope it doesn't, because we are not going to introduce a new function for the analytic continuation of it, new notation for analytic continuation of it. That would be really crazy. So we use gamma all the way, but when I write then here something like gamma of s equal to gamma of s plus 1 divided by s, I really mean what I mean. Yeah.
Tension map.
For here?
Yes.
Okay, if you don't want to use that, I give you another thing to use. So here is so what about gamma of s plus 2, for example? What is that? Isn't that equal to s plus 2? Oh, s plus 1 times gamma of s plus 1, right? S plus 1 times gamma of s plus 1, right? And then this is equal to s plus 1 times s times gamma of s, right? Now I can say gamma of s, yeah. So let gamma of s be equal to gamma of s plus 2 over s plus 1 times s. Now this is very good for real part of s bigger than minus 2, right? You can use this, right? Now, once this extended, you notice that minus 1 is a simple pole again. Minus 1 is a simple pole, right? So s equal to minus 1 is a simple pole. So let's compute the residue of gamma then at s minus 2. as s minus 1, I mean. Well, we just have to read from this formula. And we have to see what is the nature of this function around s minus 1, right? Well, there is a pole, 1 over s plus 1, which means that s minus 1 is a pole. But this guy picks value minus 1, and this is, so it means that residue is minus 1 at s equal to minus 1. So this is equal to minus 1. Make sure you understand the argument. S equal to minus 1, I put here, I still get gamma of 1, which is 1 divided by minus 1. This is like, so gamma of S looks like 1 over S plus 1 and times minus 1 near 0, near S minus 1. Oh. So this way we extended it. Now we can continue. So basically, this is a better argument to use. So I just use gamma of s plus 3 equal to, so let me write the general formula now. We just write gamma of, I mean, general formula is never good. So let's write again for s plus 3. So we just say gamma of s plus 3 now. Gamma of s plus 3 equal to s plus 2 times s plus 1 times s times gamma of s. So gamma of s equal to gamma of s plus 3 divided by s plus 2, s plus 1 times s. And what is residue? So again, minus 2, sorry, is a simple pole. What is the residue? Well, residue of gamma at s equal to minus 2 is equal to, well, I mean, this is the 1 and this is 1. You get minus 2 times this one, right? Times minus 1. So 1 over minus 2 times minus 1 is equal to 1 over 2. Yeah. 1 over s plus 1, but there is minus 1 over there too. Because this picks value at s equal to minus 1, picks value minus 1. The value of the thing is negative for this one. Yeah? I mean, this is the singular part, actually, precisely. There is a holomorphic part after that, added. You add a holomorphic part after. Is that clear? Any questions or comments? Okay, now, so you can work out now. So this we just continue forever. Just extend it forever. Yeah. Yeah, exactly. Yeah, exactly, because when we extend it, it's going to extend it here, because this value relates to this line, which is okay, except for, yeah, this line is totally okay. Yeah. For example, and so on. Yeah. All values are defined except negative integers and 0, where the gamma has a simple pole, and the function is analytic everywhere, except at those points with simple poles. And so we have to remember, but the residues are changing, and they are changing, alternating signs, right? Okay, so now the next residue, s equal to minus 3, you can see that this is going to be equal to 1 over what? Minus 3, minus 2, minus 1, right? So basically, it's going to be equal to minus 1 to the n over n factorial. So residue of gamma at s equal to minus n is going to be equal to minus 1 to the power n divided by n factorial. And this is a good formula. Actually, it's true for n equal to 0, 1, 2, 3, and so on. Right? Okay. So this way, gamma extends to all complex numbers except these things. Cannot do anything about it. Not by this method, at least. Okay, now it would be nice to have a formula that defines gamma for all values of S except these points. I believe this formula exists, but I was just too lazy to look it up. This formula exists. There is a formula that gives the values at one stroke. And in fact, I believe the first formula was discovered by Bernoulli. It was even before Euler. Bernoulli in, I think, 1720s wrote this letter to, I don't know, Euler maybe, that people were wondering about extension of factorial function to all non-integers, and here's the formula, take it. So just he writes an infinite expansion, and that's what it is, but I just don't remember this, and I don't know the proof. So, you know, have you seen the formula? Which one you have seen? Yeah, the infinite product formula. There are several of those, apparently. Yeah, I mean, Gauss has his own formula, I think.
In this case, right? Say instead of
I see. But it's finite. But the thing to write something that works for all complex numbers, you have to write an infinite product. No, I mean, what I'm saying is that does not follow from this. It must be other considerations. From this sort of observation doesn't follow that there is a formula in general. I doubt it. Because, you know, you pick an S, then there is, maybe there is, I don't see it now, yeah. Okay, so, okay, we'll talk about it later. Yeah, I'll ask you. So any other questions or comments? Okay, so I believe, well, I mean, you can give a course on gamma function, of course. There are books people have written about gamma functions, but I believe so far we are okay with gamma. So unless if you have some questions, I will then use gamma as a tool to study zeta function, yeah. That's why the reason I spend time on gamma function is because we need yeah, really. So now what we are going to do is this. So the next topic, which is actually, we already started it. I mean, so analytic continuation. And functional equation. For zeta function. So let's recall that we had zeta function, zeta of S, sum 1 over n to the s, right? So immediately obvious, well, more or less, that this is holomorphic for real part of S bigger than 1, right? That's what we had. We proved little more. Do you remember what we proved about zeta? About its analytic continuation? Yeah, we proved, yeah, what did we prove about zeta? I gave actually 2 different proofs of that fact about analytic continuation of zeta.
that could continue.
Exactly. So originally, oh, this is one. Yeah, originally this was here, and we proved that actually can be extended to here, except that one, which is singularity, which is simple, which is a pole, simple pole. Yeah. So and we had two proofs of this. One was this thing from Sir. The other one, which was I introduced this eta function alternating sum, that kind of trick, and then we used it to do this. But then I said that pushing the thing below this line, it's a lot of work. You have to have really new ideas. And yeah, so that's what we're going to do. So Riemann, in his paper, in 1859, Riemann was elected to Berlin Academy. And to thank the Academy for the honor, he submitted a paper on number theory. And this paper, this is a paper of Riemann. So it's called On the Number of Primes. I'm translating from original German by heart. I'm not sure. On the number of primes less than a given magnitude. This paper, you think, how long is it? Huh? 3 pages? Oh, a little more than that.
Very short.
Yeah, it's 9 pages, 8 or 9 pages. In English translation, I don't know. It comes a little bit longer. I'm not sure, but I think, and of course, depends on typesetting and everything. So it's original. I think it's 10 at most, but 9, I would say, pages. This paper is really amazing. So he does a lot of things in this paper. So one of the things that he does, he gives 2 proofs of. So the first thing he does is the following: 2 proofs of analytic continuation and functional equation. This was more or less new during the time. Maybe 2, 3 other people knew that this was possible at all. Yeah. 2 proofs for it. But I mean, he proved both at the same time. So they came through the same machine. Yeah. And then he did some other more amazing things. But so I'm going to give his second proof basically right now. Maybe if I'm in good mood, I will give you the first proof also. So his second proof, basically, it can be summarized as follows: the Mellin of theta is zeta. Mellin of, so it's like a slogan: Mellin of theta is zeta. So you will understand what I have in mind. This is a slogan that summarizes his proof. And I wrote it as a slogan because this slogan is repeated again and again and again in many other proofs. So that's worth remembering the message. Mellin of theta is zeta. So there are 2 functions, theta and zeta, and they are related through Mellin transform. So it's like a Fourier transform, some fancy version of Fourier transform. Fourier transform of theta, not usual Fourier transform, but some fancy other types of Fourier transform is related to zeta, of theta function is related to zeta function. Now, let's see how this works. So first of all, the first thing we remember is that lambda to the power minus s is equal to 1 over gamma of s integral 0 to infinity e to the minus lambda t, t to the s over t dt. So the first step is the following thing. For any lambda bigger than 0, and for real part of s bigger than 0. This is the essential thing that I'm going to use, lambda to the power minus s equal to 1 over gamma of s, 0 to infinity, e to the minus lambda t, t to the s over t. So let me prove this to you. I mean, this you have to remember it like this because it's going to be used again and again and again. But let me prove this for you. So proof of 1. Well, let's write the gamma function as we know it. What was gamma of s? Let's write gamma. Remember, gamma of s was integral 0 to infinity e to the minus t, t to the s over t dt, right? So now what I'm going to do, I'm going to change variable from t to lambda t. I can do that because lambda is positive. So this map sends the domain to domain, so I can do this change of variable. Then what do I get? I get gamma of s equal to integral 0 to infinity e to the power minus lambda t. Now I've got here lambda to the s, t to the s, over lambda t. Here also dt goes lambda dt, right? This cancel, and this brings to the left-hand side, you just reverse, you get lambda to the power minus s equal to 1 over gamma of s integral 0 to infinity e to the minus lambda t, t to the s over t dt. And that's what we wanted to prove. You see that? Clear? Questions? Comments? Complaints?
The spectral zeta always the same way to get its corresponding field.
From the heat kernel, yeah. That's the way, here comes heat kernel or partition function eventually, as we'll see, and here comes the zeta function. Yeah. This is the move. So this is more or less called Mellin transform. So we say Mellin transform of exponential is lambda. So, yeah. Here lambda dt, yeah. Yeah, because change of variable, t goes to lambda t, so you differentiate, so it should be lambda dt, right? Yeah. And they conveniently cancel with the denominator, and that's why we get this formula. So in particular, so this is done. So in particular, n to the power minus s is equal to 1 over gamma of s, integral from 0 to infinity. So it follows that n to the power minus s 1 over gamma s 0 to infinity e to the power minus nt t to the s over t dt. Right? So now what is that? That's for n equal to 1, 2, 3, and so on. And we just add them all for all n. Then I get on the left-hand side zeta of s is equal to 1 over gamma of s, right? Okay, so let me still write it like this. I get sum 1 over n to the s, n from 1 to infinity, equal to 1 over gamma of s, integral 0 to infinity, e to the minus t, minus, okay, sum of e to the minus nt, okay? And from 1 to infinity, t to the s over t dt, right? You see that? Sorry? N? No, n cannot be 0. It should be 1. Starts from 1. And so of course, left-hand side is zeta, and this is this sum now. So it's here that in the two proofs up to here, the same starting point. Now here there is the roads separate. You can sum this series either as is using geometric sum, and then it leads to a first proof, which uses residue theorem in a very creative way. I will call it later. Or you can do the following thing. You can change here n to n squared and see what happens. Okay. So far we have reached to that equality. So next, if we just change n to n squared, then I get sum of, so I just sum over n squared instead of all n's, or sum over all n squared. I can do that, right? So I get sum on the left-hand side, 1 over n to the power 2s, right? N from 1 to infinity is equal to 1 over gamma of s, right? Integral from 0 to infinity. So here, by the way, this is for real part of s bigger than 1, right? Because this function for us does not exist for real part of s less than 1 or equal to 1 even. This is just for real part of s bigger than 1, right? Okay, so this is the one. So now 1 over gamma of s integral 0 to infinity. And now I get sum e to the minus n squared t, n from 1 to infinity, t to the s over t dt. So then I will change s to 1/2 s. So I get on the left-hand side sum 1 over n to the s, and from 1 to infinity equal to 1 over gamma of s over 2, right? Integral from 0 to infinity sum e to the minus n squared t, and from 1 to infinity. But I said I change s to s over 2. So this is equal to t to the power s over 2 over t dt. Now this is for real part of s, obviously, again, bigger than 1. Okay, then I will change t to pi t. I'll change next t to pi t. So let's see what happens. If you change t to pi t, let's see. Then I will get, here is on the left-hand side, I have zeta function. So I get zeta of s equal to 1 over gamma of s over 2, integral from 0 to infinity, sum exponential of minus pi n squared t, right? And from 1 up to infinity. Now here, t to pi t. So pi to the power s over 2, t to the power s over 2, t to pi t. So pi t, and dt goes pi dt, right? You're okay? Yeah. Yeah, but then here I just replace s by half s. Oh, here.
Yeah.
But why you want real part of S? Oh, you mean because of this sum? Yeah, but I mean, this is okay now. This is summable. This is for real part of S bigger than 1. This is okay, this part. And this part is also okay. This is okay.
Right there.
Yeah, is that okay? Okay, so now, so far we have got this. Now, let's see. So, what I will do, I will multiply this on the left-hand side, gamma. So, gamma of S over 2. This pi I multiply by, because there's no t in pi to the S over 2. So I just bring it to the left-hand side, pi to the power minus S over 2, zeta of S. This whole thing is equal to integral from 0 to infinity. Now this function, I'm going to call it psi of t for now. Psi of t, t to the S over 2 over t dt. Okay? And this is the right-hand side. Okay? Now, this left-hand side has a name. It's such an important function. It has its own name. It's called completed zeta function. This is called completed zeta function. Let me introduce a notation for it. Riemann uses the notation xi, but writing xi on board is very difficult because it's going to be confused with zeta, especially if it's written by me. So I'm going to use another notation, capital Z. So let me introduce this notation then. Completed zeta function. It's a very, very important object. Completed zeta function. Z of S, by definition, is equal to gamma of S over 2. Pi to the power minus S over 2. Zeta of S. This is the completed zeta function. Now, this function on the right-hand side is closely related to a very famous function called theta function. So this one of your presentations will be about this theta function and their teens. So there will be hierarchy of theta functions. You will. I think your presentation is about theta functions, right? Good. And all that. So theta function. This was introduced again. It's hard to say who introduced it first, but maybe I just say Jacobi's theta function of third kind. Again, not completely in this form, but it's essentially this form theta of t I just used is sum e to the minus pi n squared t, but n goes from minus infinity to plus infinity. This is the famous theta function of Jacobi's theta function of third kind. Jacobi had a list of theta functions, first kind, second kind, third kind. I don't know if there was a fourth kind or not, but then he wrote lots of other things in terms of those theta functions. But this is the, and then Riemann picked up this as the basic theta function in his work. He extended it again and again and again to many contexts. But this was, so now let's look at that function. First of all, that function is, you see that it's defined for real part of t positive, right? This is defined for real part of t positive. I mean, if you don't want it, that's okay. You can look at it only for real t, because here we are integrating over only real values of t. But in reality, this function exists for all complex numbers whose real part is positive, right? And this series is actually a rapidly convergent series, because as n goes to infinity, this declines exponentially fast. The general term of the series goes very fast. And what is the value of this function at t equal to infinity, you think? Can you tell me what is the value of function at t equal to infinity? Is it 0? 1? Why? You looked at something? Oh, you look at, oh yeah, because it looks like it's going to go approach 1. Okay, any other guesses? Yeah, it would be 0 except for the constant term. There's a constant term. You see, if you look at theta of t, there is a term 1, right? And then it's symmetric for t and minus t are the same. So I can just write it as twice. And in fact, this is what Riemann had. So sum exponential of minus pi n squared t, and from 1 to infinity. You see, you agree with me, right? And this is Riemann's psi t, right? This is psi t here. This is psi t. One thing, first of all, we connect to Riemann, and now we know why Riemann did these moves, strange moves, because he wanted to reach to his beloved theta function, because he knew he could do something with theta function that no other function can do for him. And that's what we'll see now. But this is psi t. Now, also the limit as t goes to infinity, obviously, this part goes to 0 because all these terms rapidly go to 0. All terms go to 0. And this is 1. So this is the constant. Okay. So, and in fact, theta function for real values of the things looks like this. It rapidly, this is 1, rapidly goes to 0. And of course, as t goes to 0, these guys approach to 1. So they go to infinity. So they go to infinity. But do you know how fast it goes to infinity? Is it going like 1 over t, 1 over t squared? Is it going like a log of absolute value of log t, or 1 over root t, or some crazy function? It's very hard to know how fast it goes to infinity at 0. It's extremely hard to know. This is psi of t, and we have to know that, actually. Okay, I give $5 to the person who can have the right guess. 1 over ln? 1 over ln? No, it's not. No, 1 over ln, wait a minute. I mean, 1 over ln, as it goes to 0 as t goes to 0. It doesn't go to infinity. You have to have something that goes to infinity. It actually goes to, yeah, goes to 0, definitely. Because ln t goes to 0, 1 over, it goes to infinity. No, yeah, it goes to 0, because ln t as t goes to 0 goes to minus infinity, and that's the inverse. So that's out. Okay, I won't punish you by, what else? Any other guesses? But that's also, I mean, negative ln t. Yeah, this is positive infinity. No, it's not ln. Get out of ln business. Get out of my lawn. Yeah. Yeah, I think, yeah, the thing is, this is going to infinity like 1 over root t. That's very hard to know. So yeah, it's related to Gaussian. These are sums of Gaussians in n, though, not in t, unfortunately. That's okay. Yeah, Gaussian is behind the scene, is doing something for us here. Okay, so now we are here, and then what Riemann says that I know a functional equation for theta. So let me write it down, and then we'll continue the proof. So the next step is to use functional equation for theta. So theorem, functional equation for theta. Riemann says that this is Jacobi, is due to Jacobi, and he gives a reference, actually. Maybe that's the only reference in his paper, but you open that paper, is not there. And in another paper of Jacobi, there is a reference to this result, but he attributes it to Poisson. So it's just so anyhow, this is also called so this is maybe Jacobi, Poisson, and some other guys, but this is basically is modularity property. So this is the modular invariance of theta. So what is it? It says that theta of t is equal to 1 root t, theta of 1 over t. For t positive. So theta of t is equal to 1 over root t, theta of 1 over t. Of course, immediate corollary of this is that theta of t, as t goes to 0, this is 1 over root t. Theta of 1 over t, as t goes to 0, goes to 1. You know that, right? So this is asymptotic to 1 over root t as t goes to 0. So this gives you, among other things, the asymptotics of how fast theta grows near 0 by this. But it's not just asymptotic. It's exact equality of two sides. That's the amazing thing. This is equal to that. And if you write it, you try to prove it. There's no way to prove this. You will be hard-pressed to prove this, because what it says, it just says some exponential of minus n squared pi t. I just wrote it the other way around. Or n in z is equal to 1 over root t sum exponential of minus n squared pi 1 over t. My God. This is one of those things maybe Ramanujan perhaps could do over a t or something, but after many years of working on these things in his notebook. But it's not something that you would start working on it and then finish it in, I don't know, 10 months or something. I mean, this is very, very strange formula. Very, 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 very strange formula. Huh? No. So this I will prove later. So first of all, proof later, because I don't want to break the proof of Riemann's functional equation by going into the proof of this in the middle of a proof of another thing. But this is something that you have to try to appreciate for yourself first, and then we'll prove it later on. But let's use this now, okay? So now, in terms of, so this is psi of t, right? So in terms of theta, then psi of t is equal to what? Let's write it down. Psi of t is equal to, yeah, we're good with time. So what we've got is that psi of t that appears is equal to theta t minus 1 over 2, right? That's what we have. Okay, and then what I erased here up to that point basically said that z of t, we have proved so far the following relation. So the story so far is that we have got this far. Zs, sorry, is equal to integral from 0 to infinity. What did we have? Psi t, which means theta of t minus 1 over 2, right? Over 2. And then t to the s over 2 divided by t dt, right? T to the s over 2 divided by t dt. Yeah. That's the completed zeta function that has 3 terms, right? Pi, do you remember those terms? Gamma of s over 2. Gamma of, don't confuse s with t, because this will just send me mad. So gamma of s over 2, pi to the power minus s over 2, zeta of s. 2s over 2, 1s. 3 factors. Those factors are very, very important. They have actually geometric topological meaning. They have to do with boundaries of some curves. But you don't see it now. Yeah, anyhow, that's why it's called completed, because it means that there was some curve which was not complete. You added the boundary, you made it complete. This way. This is the geometric picture behind that, but that's okay. So now we have 2z of s. I just write it like this, equal to integral 0 to infinity, theta of t minus 1 times t to the power s over 2 over t dt, right? We have so far. Are you okay with it so far? Now, what we are going to do, we are going to write this using this relation, the modular property of theta. So I'm going to break the integral into 2 pieces, from 0 to 1 and from 1 to infinity. So this I just write it as integral from 0 to 1, theta of t minus 1, t to the s over 2 over t dt, plus integral from 0 to infinity, right? Theta of t minus 1. 1 to infinity, yes. Yeah, 1 to infinity. Theta of t minus 1, t to the s over 2 over t dt. So let's call this term A and this term B. Yes. Yes, that functional equation holds for all values of this. But if you, it's here. So this is 1. It's the importance of integration from 1 to infinity that we want to exploit. Now you will see why. Because let's look at term B. What is the nature of this term B? You see, theta, I mean, this is, first of all, there is no 0 singularity here. We just discarded the singularity at 0. It starts at 1. So these functions are just fine. We don't have to worry. The only thing to worry about of this integral is integration at infinity, right? Is the infinite limit. Can you tell me if, for what values of S this integral is convergent? This integral, B. For which values of S this integral is convergent? So far, real part of S was bigger than 1, right? Because everything is bigger than 1. I mean, theta is, I mean, this is for real part of S bigger than 1 so far. But what about this integral B? What can you say about B? Where is it convergent? For what values of S? You see, there are two factors here. Theta t minus 1, how does it behave at infinity? Theta t minus 1. It's rapidly going to 0 because we subtracted the constant term, right? So this is rapidly going to 0. This is exponential decay at infinity. And t to the s over 2 over t, it's just a polynomial in s over 2 minus 1, our s over 2 minus 1. No matter what s is, this is convergent and a holomorphic function. So B is already a holomorphic function. And that's really huge progress already. At least part of the this you have shown that is actually is defined everywhere, not just some. It's just this part is defined. Okay, so let me write it. This is holomorphic. So this part is holomorphic on C. Now we are going to do the same thing to this part by using this transformation of t to 1 over t. So we switch 0, 1 to 1 to infinity by doing this method. So now all we have to do, we have to concentrate on A. Now I'm going to concentrate on A. Okay, and A, of course, this is our guiding equation that will take us through these stormy waters. So let's see, A is equal to integral from 0 to 1, theta of t minus 1, t to the power s over 2 over t dt. Now change variable t to 1 over t, right? If you change variable t to 1 over t, what do we get? A becomes integral from 1 to infinity, theta of 1 over t minus 1. This is t to the power minus s over 2 times t, because this is 1 over t, and dt is dt over t squared. Okay with this? So this is equal to now integral from 1 to infinity, theta of 1 over t minus 1 times t to the power minus s over 2 over t dt if you want. Huh? You okay with this or no? What happens to the sign of the derivative? Yes, if you do that, you change the orientation. You start from infinity to 0. So I change it to, I mean, infinity to 1. I change it to 1 to infinity, but I compensate it by that sign of minus 1. So that's okay. So far, okay, right? So far, so good. Okay. Question? Now I'm going to use Poisson's or Jacobi's identity for theta of 1 over t. So I just replace it by What is theta of 1 over t? Well, theta of t was equal to 1 over root t theta of 1 over t. So that's root t theta of t. Okay? So that's root t theta of t minus 1 times t to the power minus s over 2 over t dt. So now I'm going to do the following thing. First of all, I just write it as integral from 1 to infinity root t theta of t. Okay, so I just multiply this by that. I'm going to get theta of t times t to the power minus s over 2 plus half here, plus half, factor of half here, divided by t dt. And then there is this, this part minus integral from 1 to infinity t to the power minus s over 2 over t dt. Yeah, you're okay? This integral I can compute. Okay, so what is this integral? Just tell me. Okay, so now here, okay, so I'm going to do the following thing. I'm going to subtract and add 1 here because I want to subtract that constant term. That's a nuisance. So I subtract and add that constant term. So I just get this equal to so then what I'll do is the following. So this is equal to integral from 1 to infinity theta t minus 1 plus 1 t to the power minus s over 2 plus 1, right? Oh, not plus 1, plus half. Plus half over t dt plus, now let's compute this integral. Let's not let it linger around, so to speak. This is what? T to the power minus s over 2 minus 1. So this is 1 over minus s over 2, t to the power minus s over 2 from 1 to infinity, right? Is that okay? This is the antiderivative I'm saying, because if I take derivative of this, it's going to be, okay, minus s over 2, then minus s over 2 minus 1. Yeah, this is okay. This is okay. So I compute at infinity, this is 0. Now, remember, real part of s is bigger than 1 at least for now. So this is 0 at infinity, and at 1 is going to be 2 over s. So this part is 2 over s. Yeah. With the minus sign. Oh, we have to be careful about the minus sign, though. No, no, no. I'm off by minus sign, I guess. I just did this. But there's a minus. And so I think I should put minus.
Minus.
Huh? No, no, no.
There's 3 minuses.
There are 3 minuses.
There
There are 3 minuses. Yeah, yeah. Should be minus 2. Just verify. Don't believe me. Verify that for yourself. Yeah. Okay. So now I just write it. This is all A. Remember, 1 to infinity theta t minus 1 t to the power minus s over 2 plus half divided by t dt minus, okay, plus again another integral I have, integral from 1 to infinity. This also I can compute, t to the power s over 2 plus half. Okay, rather minus half because I want to compute this now. This is, oh no, that's okay, over t, and this is dt minus 2 over s. Okay, so this is equal to integral from 1 to infinity theta t minus 1 t to the power minus s over 2 plus half over t dt. Now, what is this integral? This integral is 1 over s over 2 plus 1. T to the power s over 2 plus 1 from 1 to infinity, right? That's just the antiderivative. I mean, if you think about it, this is s over 2 plus 1 here. And then there should be a negative sign. I made a mistake somewhere. Well, why did I not write? Okay, I made a mistake. This is minus s over 2. Yeah, sorry. Yeah, minus s over 2. Minus s over 2. This is good. Okay? Minus s over 2 plus 1, t to the power minus. So. Oh, this is half. This should be half. This should be half. Maybe that's why you were lost. Huh? And then there is minus 2 over s. What? Which one? Here?
Yeah.
I just added and subtracted.
Oh, that other term. Okay.
The terms less the same. Add and because I want to subtract the constant term from theta so that at infinity behaves well. Otherwise, I'm cursed at infinity. Okay? Any questions or comments? Okay. Yeah. This one, you mean? Yeah. That's what we want. That's what we want, yeah. Yeah, this is negative S over. I corrected it here, but I forgot to correct it here. This is negative S over 2. This is negative S over 2, yeah. That's what you meant, right? Yeah, good. Yeah, it's negative. Okay, almost there, not there, but almost. So the completed zeta function was sum of two terms, a and b. B, I said we keep it because this is nice, holomorphic function. Just keep it. This is the troubled one, but so far we have shown that the troubled part is equal to this one now. So this is A. So let's write everything now in one formula, see what we have got. So I've got now Z, the completed zeta function of S. So we have got that the completed zeta function Z of S is equal to, first of all, there is this part, right? The integral 1 to infinity theta of t minus 1 times t to the power negative s over 2 plus 1 divided by t dt. Let's compute this term. Huh? Oh, 2z of s, yes. Very good. Yeah, thank you. It's 2z of s is equal to this. Now let's compute this term. What is this term? This term as infinity, again, is 0 because real part of s is bigger than 1 or whatever. And at 1, you're going to get 1. But the minus sign. So this is minus 1 over negative s over 2 plus 1, right? So this is minus 1 over, let's be careful, minus negative s over 2 plus half again. Sorry? Oh, yeah. Okay, very good. And then what about this one? Negative 2 over s. That's also there. And b, we should not forget about b, plus this term, 1 to infinity, theta of t minus 1 times t to the s over 2 over t dt. Sorry?
Negative s over plus.
Mhm.
Negative s over plus.
Why?
This-
Oh, this is this one. Oh, yeah, yeah. Okay, good, 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 good. Yeah, actually, it's much better. Yeah, that's what I need. Right. Good. Okay, now, as you said, this part is what? 2 over 1 minus s. Is that what you said? This is 2 over 1 minus s, right?
S.
S minus 1, even better. Yeah, yeah, yeah. So this is 2 over s minus 1, negative or positive? Positive. Huh. Well, minus 2 over s. Okay, so, okay. Okay. Now, what can we say? Now, in front of us, we have everything we need. So this is a really low-lying fruit. Now you have to pick up the cherries. Something amazing is in front of you now. Sorry. These two terms combined? You can, but let's see first of all. What can you say about, first of all, analytic continuation of z? Completed zeta function. What can you say about analytic continuation? So I'm asking now, we started from functions that only existed for real part of s bigger than 1. Now I have written the same function like this. Where is the domain of convergence of these integrals and the function on the right-hand side? Is everywhere except, okay, this is everywhere, but we have these two poles, s equal to 1 and s equal to 0. So this is really amazing now. So it means that z function has analytic continuation to the whole complex plane except at s equal to 0 and s equal to 1. No, we know that. But we are confirmed again by this method here also. Yeah. So the first corollary is that z of s has analytic continuation to c minus the 2.01, which is these two things, s minus 1 and 2 over s. Now, the second one is that corollary 2, which is, so this is, will give us analytic continuation. But the second corollary is even more amazing. This function is symmetric under change of s to 1 minus s. Z of s equal to z of 1 minus s. Let's see why. First of all, let's check this. Check what happens to these two functions. We have these two functions, 2 over s minus 1, minus 2 over s, right? If you change s to 1 minus s, what do we get? We get 2, 1 minus s minus 1, minus 2 over 1 minus s. And that's exactly the same as the thing that we started with. Because this is minus 2 over s, which is here. And this is 2 over s minus 1, which is here. So this rational function, this rational part, which corresponds to poles at 0 and 1, already is symmetric under the transformation zs equal to z1 minus s. This part is already satisfied the property. So it drops out the picture. Now we have to look at these two things. Of course, there is no s here in theta. You just have to look at these parts. And that's what you notice, I think. So let's look at these parts. What happens here? The same. So let me just check. So let's check now.
Green light. Over 2 plus 1/2 as 1 minus s.
Huh?
Light negative
Mhm.
plus half.
Mhm.
1.
Oh, that helps, you think? Okay.
It's very clear.
Yeah, sure. I mean, this is really, for what I'm saying is that this is t. First of all, I'm going to keep this t in the denominator, not creating more factors. And then in the numerator, we have got 1 minus s over 2, right? Another factor here is s over 2. Now, if you change s to 1 minus s, what do you get? You get t to the power 1 minus s over 2. I mean, it's not plus. And then t to the power 1 minus s over symmetric. That's it. So it shows that this is the functional equation for zeta function. This is not the form that Riemann wrote. He used the reflection formula and he wrote it in terms of sine because there's a relation between sine and zeta function. That's not the way he wrote, but that's exactly equivalent, no more, no less than this one. So let me just write corollary and then we take a quick break. So maybe not so quick because we have to spend. So the corollary is that, so this is functional equation and analytic continuation. Of zeta function. So zeta of s can be analytically continued. Now I say to c minus 1 is okay at 0. To c minus 1 and satisfies this equation z. So I just write it like this. Pi, the power minus s over 2, gamma of s over 2, zeta of s is equal to pi to the power minus 1 minus s over 2, gamma of 1 minus s over 2 is zeta of 1 minus s. This looks strange, but that's what we did. And Riemann wrote it something equivalent to this, but with different notation for formula for gamma. His gamma factor was a bit okay. No, I mean his gamma factor is gamma factor, but I mean yeah. You should read Riemann's paper, translated to me. So the only thing that's missing is why c minus 1. Why I say zeta is okay at 0, is analytic at 0. Because z is not analytic at 0 because z has a pole at 0. That's the only thing that remains to be proved, right? You see? So why this thing is, why zeta is analytic at 0? unlike Z. Hmm? This is Z. Yeah.
S.
Gamma at 0 has a pole. Gamma at 0 has a pole of order 1, simple pole of residue 1. That's we know. This is S over 2, of course, but that's same. Okay, if Z had a singularity at 0, this would add to the singularity of Z at 0. But we know that Z has simple pole at 0. So Z is regular. Zeta is regular as 0. You see the argument? This is very, very important now. You have to realize the product is singular at S equal to 0. This is also singular of order 1, both order 1, so this has to be regular. Order 2 at least. Yeah, singular. But we know it's not true. Yeah, that's one of the things that. Okay, so that's the end of the proof. So this is the second proof. Now you're at page 3 or 4 of Riemann's paper. He has already given first proof in the first 2 pages, 2.5 maybe. This is almost 1 page, less than a page, half a page. So I believe up to page 4, 4.5 is true with 2 proofs of functional equation and anti-continuation. Of course, you might ask yourself, and it's a very good question, so what? Well, what is the reason? How we are going to use this? What it has to do with anything about prime numbers? I mean, what was his motivation? Yeah, we'll see those gradually. But just as a question of analysis, it's really amazing that this function that we had no idea it can be analytically continued. It has an anti-continuation, and it has this amazing symmetry, which is quite a simple type of symmetry. So we will come back and derive some more immediate corollaries of this, and then I owe you a proof of Jacobi's identity, theta of 1 over t, theta of t equal to 1 over root t, theta of 1 over t. This will prove. Okay, so I think we can pause now. Maybe you can ask questions if you want. So let's just pause. I mean, just a second, please. I just want to stop recording now. Okay, so pause. Oh, recording. Yeah, good. So let's wrap it up now towards. So far, what we have got is this. So we have z of s equal to this is the completed zeta function I to the power minus s over 2, gamma of s over 2, zeta of s. Okay, so we saw that is holomorphic. In C, take away 0 and 1. Now, one corollary is that, of course, as we said, zeta can be analytically continued to the whole complex plane except 0. Now, another corollary is that zeta at negative 2n is 0. For n equal to 1, 2. So zeta is 0 as negative even integers. Why is that? Yeah, because you see, the whole thing is analytic at these points, right? At negative 2n. And gamma has a pole, simple pole, at negative integers. So it means that zeta has negative even integers, because s over 2 has to be integers, so s has to be even. So zeta is, okay, so proof gamma of minus 2n over 2 is equal to infinite, it's a simple pole. This implies that zeta of minus 2n is equal to 2. So this is the source of fund relations like 1 over 2 plus 2 over 2 plus 3 over 2 plus 4 over 2 equal to 0. Then people say 1 over 4 plus 2 over 4 plus 3 over 4, 4 over 4. These are the relations people write, right? Just to amuse you. But that's what they mean. Because formally, if you substitute, what they do, they substitute these values into the original definition of zeta on the right half plane. And then they write these formulas. Which is, of course, illegal because the formula that we have on the right-hand side is not valid on the left-hand side. So that's an illegal thing, but it gives some fun. Yeah. Zeta? Oh, we did already check it. Look, this function, oh, you mean this one? Oh, yeah, okay. Yeah, there's some point here. Yeah, okay. Right. So maybe this is corollary 1, or I don't know what, for now, corollary 1. But let me write corollary 0. Yeah, that's a good point. I think that's what you mean. I'm not sure. Maybe that's what you mean. Corollary 0 is that actually zeta of s is holomorphic everywhere except at s equal to 1. Well, but I didn't give a complete proof. I should tell you. Yeah. Yeah, you see why? You see, this product, yes, is holomorphic, right? So let me give a proof. We know that pi to the power minus s over 2, gamma of s over 2, zeta of s is holomorphic, right? This is z of s. This is holomorphic in C minus 0, 1. So what we want to do, we want to write zeta of s as z of s divided by this function. But I have to be able to divide by this. Because if this gamma has some zeros, then it will kill the joy, because zeta can have poles at those points that zeta has zeros, gamma has zeros, and then it will just create problems for us. But that's not going to happen. The reason is that gamma is never 0. That's the thing. So did you see what's the argument? I mean, you see that? There's a point here we have to establish. Okay, but gamma of s is different from 0. That's what I wanted to mention, actually. I should have mentioned when I was wrapping up the discussion of gamma, I should have written this. But gamma of S is different from 0 for all S belonging to C. That is defined, actually. So the proof of this is a bit difficult, actually. I don't think I will prove it, but I give you some idea why this might be true, actually, but I can't prove it now. But I tell you what's going on. Okay, so suffices prove this for real part of S bigger than 0, because I mean, otherwise this is defined through this by dividing by 1 over S, S plus 1, and so on, right? But what is zeta of S? Sorry, gamma of S. Well, this was 0 to infinity, e to the minus t, t to the s over t dt. Now, you can see that this function has no zeros for S real. This is obvious. Obviously, I say gamma of S is different from 0 for all S positive real. I mean, this is okay. But we need to know that actually gamma is not 0 anywhere else. That's very, very important. Otherwise, I cannot say that zeta is holomorphic. Are they? I mean, so let's finish now. Okay, so we will continue this next time. Anyhow, our time is up, so we should finish anyhow. Okay, guys. So I'm just finishing. Okay.